Have you ever been in that situation, maybe making a really big investment decision, like for a critical piece of machinery on your shop floor, and you're looking at two options, and honestly, on the surface, they sound almost the same. Both promise, combined turning and milling, but you're told, no, no, they're fundamentally different, and picking the wrong one, that could sink your project, blow your budget. It's that feeling, right? The confusion, the pressure, the risk of wasting a huge investment. I think we've all felt that. Well, today we're doing a deep dive into exactly that kind of dilemma, but specifically in the world of precision manufacturing. We're going to pull back the curtain on two really powerful machines, the Swiss lathe and the turn mill center. Our mission, basically to cut through all the technical jargon, we want to reveal the core philosophy behind each machine to help you, our listener, understand exactly when you choose one and why. Because, let's be real, choosing wrong here isn't just a small mistake. It could mean spending hundreds of thousands on a machine that's, well, either total overkill for your parts, or worse, maybe it just can't hit the quality or the efficiency you actually need. So think of this as like your shortcut to getting really well informed about a super critical decision in advanced manufacturing. We're aiming for those aha moments, the surprising facts that really highlight the genius of mechanical engineering and show you why a machine's design philosophy matters way more than just the specs on a sheet. Okay, so let's unpack this. A Swiss lathe, a turn mill center. They both turn things, they both mill things, they process material, often bar stock, but we keep hearing there's this huge fundamental difference, almost like a philosophical divide in how they approach making a part. What really is that core distinction? And why does something like the part's length to diameter ratio, how skinny it is, why is it so important here?
Yeah, it's fascinating, isn't it? Because the difference isn't just features. It's not just bells and whistles. It's the whole design philosophy, how the machine thinks about the part. You could almost picture them as two different kinds of experts. The Swiss lathe, that's your ultimate specialist. Its main job, almost its only job, is solving that really tough problem. How do you control vibration and bending when you're machining long, thin parts? And it does this with a really clever sliding headstock and this thing called the guide bushing. It supports the material right where the cutting happens.
Yeah.
That's how it gets that extreme precision.
Okay, so hyper-focused, a specialist.
Exactly. Now, the turn mill center, that's your super capable generalist. Think of it as more robust, much more versatile. Usually have a multi-axis, B-axis milling spindle, and its whole design is about bringing a massive amount of, well, multi-axis capability to complex parts, often bigger parts too. The goal is to make the whole part, no matter how complex, in just one setup. So yeah, it's a fundamental split. Yeah. Specialized focus versus broad, complex capability.
That specialist versus generalist idea, and thinking about the core philosophy. That really helps clarify things, big picture anyway. But to really get how they do it, we need to dig into the actual mechanisms, right? Because we hear these terms thrown around, guide bushing, B-axis spindle. They sound super technical. What do they really mean for how the machines work? And, for our listener, why should they care about the difference beyond just the tech speak?
That's a really important point. Because if you confuse these two, you fundamentally misunderstand what each machine is actually built for. You miss where its real strength lies. So let's break them down. They couldn't be more different in what they're trying to achieve. The guide bushing, that's the heart of the Swiss lathe, really. It's basically a workpiece support mechanism. Imagine like a super rigid collar, okay? It clamps down tightly on that thin raw material right next to where the tool is cutting. Its entire job is just unwavering stability. It physically stops that slender material from bending or chattering.
Ah, chatter, that horrible noise.
Exactly. That awful vibration that sounds terrible and just ruins the part finish. The guide bushing prevents that. It's actually designed very cleverly. It rotates perfectly in sync with the main spindle, constantly gripping the material. So any vibration, any deflection is basically eliminated. Doesn't matter how long or thin the part is.
So wait, the really mind-blowing thing here is, for those super tricky, long, thin parts, the key to precision isn't some super complex motion. It's actually about simplifying by just providing massive stability right at the cut. That seems almost counterintuitive.
It really is. Less unsupported movement equals more precision for these specific shapes. Now compare that to the B-axis spindle you find in turn mill centers. Completely different animal. This isn't about support, it's all about flexibility. Imagine a powerful milling head that can tilt and swivel. It lets the cutting tool come at the workpiece from almost any compound angle you can imagine. Combine that with the machine's standard linear axis XYZ and the rotating C-axis of the main spindle, well, you effectively get simultaneous control over all 5 axes.
So true 5-axis machining.
Exactly, for really sculpted parts. Its purpose is the versatility you need for complex curves, angled holes, intricate features, things you just couldn't do on a standard lathe, let alone a Swiss.
And with that B-axis, the aha moment for me is how it changes the workflow. It's not just reaching tricky angles, it's about getting rid of multiple setups.
Yeah.
Right? Cutting down potential errors, basically turning one machine into a whole production line for complex stuff, all in one clamping.
Precisely. Done in one machining. I actually had a client once, good example. He came to me needing to make these long, very thin medical shafts, needed incredibly tight tolerances. It got exact size, perfect geometry, and a flawless surface finish.
Right. Critical for medical parts.
Absolutely.
Yeah.
And he was seriously looking at this huge, expensive turn mill center. Why? He was just blown away by its B-axis capabilities. He figured more axis must mean more capability, better parts. I had to kind of gently explain that for his specific parts, that B-axis. Totally irrelevant. Overkill.
Yeah.
What he actually needed was that simple but absolutely essential rigid support from a guide bushing. That was the only way to get the precision for those skinny medical bits.
Wow.
So you see, it really boils down to single point support for stability versus multi-axis flexibility for complex geometry. Very different goals.
That client story is perfect. Really hits home the difference between what you need and what looks impressive on paper. But I gotta ask, are there any edge cases, like maybe with super clever fixtures or specific materials, could you technically make a long, thin part on a turn mill, even if it's totally the wrong tool? Or is it just a non-start?
That's a fair question.
Yeah.
And, theoretically, maybe. With a lot of manual babying, custom supports, incredibly slow cutting speeds, you might attempt it. But honestly, it would be astronomically expensive, painfully slow, and your chances of actually hitting those tight tolerances very, very low.
So, practically speaking.
Practically speaking, it's a non-starter for anything like real production. You'd probably spend more on custom fixtures and scrap parts than the Swiss lathe would cost in the first place. That classic case, right?
Yeah.
Using a sledgehammer to drive a thumbtack and then wondering why the wall's smashed and the tack is bent.
Right. Okay, so what does this all mean when you're actually making parts? You mentioned those long, skinny parts. Anyone who's tried machining thin stuff knows this is just a nightmare. How does the Swiss lathe specifically conquer that challenge, make it not just doable, but precise and efficient?
Yeah, this is where the Swiss machine and its guide bushing really shine. It's kind of magical, actually. See, on a normal lathe, if you try to turn anything where the length to diameter ratio, how much longer it is than it is wide, gets over, say, 3:1, well, it's usually a recipe for disaster.
Disaster.
Meaning the part bends under the cutting force. It chatters uncontrollably. You end up with terrible tolerances, bad surface finish, just scrap. Expensive, frustrating scrap. The Swiss lathe, it completely sidesteps that whole problem.
Yeah.
Because that guide bushing gives rigid support just millimeters away from the cutting tool.
Yeah.
So as the raw material feeds out from the headstock, the cutting tool is always working on a very short, perfectly supported section. This brilliant design just eliminates the deflection, eliminates the vibration, even if the part's got a crazy 20:1 length to diameter ratio.
20:1.
Wow, think about it. It doesn't matter if the final part is, say, 200 millimeters long. The bit being actually machined at any single moment. It's only unsupported for maybe a millimeter or two.
Okay, that idea that the headstock moves the material through the fixed guide bushing instead of the tools moving along the part, that's just brilliant engineering. It totally flips the script for those specific parts, makes something that seemed impossible suddenly routine and precise.
It absolutely does. That's the key mechanical design. It guarantees the cutting forces always hit originally held section, which means you get incredible accuracy. That's why they're used for things like tiny medical implants, delicate aerospace pins, critical electronic connectors.
Parts where even a tiny error means failure?
Exactly. Parts where microns matter.
Okay, we've gone deep into the mechanics, the engineering genius, how they solve different problems. But, anyone who's spent time on a shop floor knows a machine is only as good as the person running it, right?
Yeah.
The operator. So beyond the iron and steel, what about the human element? Are the skills needed for these two very different philosophies of machining? Are they as different as the machines?
Oh, absolutely. Worlds apart. I mean, both jobs need high-level skills, incredible attention to detail, of course. But the programming logic, the setup process, even just the basic mindset of a Swiss lathe operator versus a multi-axis turn mill operator, completely different. You put the wrong operator on the wrong machine, you're asking for crashes, expensive scrap, terrible cycle times, it just won't work efficiently. Take the Swiss lathe operator. Beyond just the programming, which can be complex in its own way, their mindset is all about optimizing for speed and consistency. Extreme focus. They're like, a conductor, orchestrating multiple tools, often cutting at the same time, main spindle, sub-spindle, maybe tool gangs.
A lot going on simultaneously.
A real dance of synchronized moves, always thinking. How do I shave off fractions of a second? How do I keep every single part out of potentially millions absolutely identical? And their key physical skill. Mastering that guide bushing setup, getting the pressure just right for the material, not too loose so it slips, not too tight so it scratches the surface. It's an art. The whole machine setup is geared for high-speed, continuous bar feeding. That's how you get that rapid, high-volume output.
Okay, conductor for the Swiss. What about the turn mill?
Right, now switch gears. The turn mill operator. Their mindset, it's more like a complex problem solver, maybe even a sculptor. Their programming involves managing incredibly complex 5-axis simultaneous motion. You need serious 3D spatial thinking. You're constantly visualizing this intricate 3D shape, figuring out the best sequence of cuts, the tool paths from all these different angles to get that perfect done in one part.
Much more about geometry and strategy.
Exactly. And their main physical skill. It shifts towards the art of workpiece fixturing for these complex, often unique parts. How do you hold this weird shape securely? And then managing a huge, diverse library of tools in the machine's automatic tool changer, because every job might be different. The machine setup is optimized more for lower volumes, diverse jobs, quick changeovers, reflecting that generalist nature.
So it really isn't just about the machine's capabilities. It's deeply tied to the specialized human expertise, the whole way of thinking behind the operation.
Absolutely. You can have the best machine in the world, but with the wrong operator, or an operator with the wrong mindset for that machine.
Yeah.
It's just not going to perform. The best person for a Swiss is likely not the best person for a complex turn mill, and vice versa.
Yeah. Okay, so ultimately for you, our listener, it boils down to making the right choice. For your part, your production needs your budget. How do we put all this insight into action? What are the key questions you absolutely need to ask when you're standing at that fork in the road? Swiss lathe or turn mill center? Because honestly, before this conversation, I might have just glanced at the spec sheet, made a superficial call, but it's clearly way, way more nuanced. It demands a more philosophical approach to picking the right tool.
That's exactly it. And if we tie this back to the big picture, that investment decision,
Yeah.
it really comes down to 3 key things: the shape of your part, its size, and crucially, how many you need to make. I walk clients through this thought process constantly. Because remember, picking a huge, expensive turn mill for a simple little pin you need millions of. That's not just wasteful.
You're paying for flexibility you'll never use.
Precisely. Your part cost goes way up, you're suddenly not competitive, and the flip side is just as bad. Trying to force some complex aerospace valve body onto a basic Swiss lathe. Impossible. Or, okay, maybe possible with tons of extra steps. Manual work.
Working out any savings from the cheaper machine.
Exactly. Your labor costs and lead times explode. So let's make it concrete. You should choose a Swiss lathe if your parts are simple-ish to complex, but they are long and slender. That high length to diameter ratio is the key identifier. Typically, these parts are small diameter, usually under maybe 38 millimeters, give or take. And production volume, this is critical. Swiss is ideal for high volume, mass production, thousands, millions of parts. Its huge advantage is that unmatched stability and speed for those long, thin parts, which means the lowest possible cost per part, faster cycles, less scrap. Plus, the initial investment is generally lower, maybe, $70,000 to $150,000 ballpark.
Okay, clear case for the Swiss. Now, the turn mill.
Right. You choose a turn mill center. Yes, your parts have really complex geometry. Think multi-sided features, angled holes, fancy 3D contoured surfaces. These machines aren't limited by slenderness. They can handle a wide range of diameters, small to very large. Production volume here. It's ideal for lower to medium volumes. Prototypes, R&D work, jobs where flexibility is more important than raw speed. Their key advantage is that ultimate flexibility. Getting complex parts done in one. That's huge value because you avoid secondary ops, extra setups, all the potential errors that creep in when you move parts around.
But be prepared for the cost.
Definitely. Be prepared for a higher initial investment, usually over $150,000, and honestly, often much, much higher depending on the capability.
That decision matrix really lays it out. So if I'm getting this right, it's almost never about which machine could technically make the part. It's about which one does it efficiently, cost-effectively, and hits the quality needed for that specific part profile.
You got it.
And the cost of getting that wrong just seems massive. For you, the listener, whether you own the shop, design the parts, or manage the money, understanding these differences isn't just about machine specs. It's fundamental to your bottom line, your competitiveness. It really makes me think of that old saying, if all you have is a hammer, everything looks like a nail. In manufacturing, having the wrong kind of hammer for a specialist nail sounds like a recipe for some very expensive mistakes.
Well put.
So we've seen how understanding a machine's core philosophy, is it a specialist built for one tough problem, or a generalist built for wide-ranging flexibility? How that makes all the difference. The Swiss lathe, production powerhouse for small, long, skinny parts, speed and precision. The turn mill center, your versatile ace for complex, multi-sided parts, ultimate machining flexibility. Which kind of leaves us with a final thought. Where else, maybe in your work or even your life, might you be using a generalist approach when what you really need is a specialist tool? Or maybe the other way around. How does this whole idea, understanding specialized design versus versatile capability, how does that play out in other areas, affecting efficiency, cost, maybe even innovation? Something for you to chew on.